Of all the objects in the cosmos, planets, stars, galaxies, none are as strange, mysterious, or powerful as black holes. A black hole can swallow a star completely intact. But what exactly are they? If we can visit one, what might we see? With their immense power, do black holes somehow shape the very structure of the universe? Is it possible we might not exist without them? Black holes are apocalyptic objects in the universe. Engines of destruction, menacing and mysterious. Black holes. Even scientists who study them find them astonishing. They're completely invisible, yet powerful beyond imagining. They can tear a star to shreds. Black holes even slow time. Once thought too strange to be real, black holes shatter our very understanding of physics. But we're learning they may somehow be necessary for the universe we know to exist. What are these strange, powerful objects? Outrageous and surprising. Where are and how do they control the universe? The search for black holes is on, and it will be a wild ride across the cosmos to places where everything you think you know is a challenge, where space and time, even reality, are stranger than fiction. And we're starting that journey at a very unlikely place, here at a remote location in Washington state, where for the first time, a radical new experiment has detected black hole gravitational waves. It originated over 50 years ago when a few visionary scientists imagined a technology that hasn't yet been invented. Searching for something no one is certain can be found. The experiment is daring and risky. Failure could mark their lives forever, but they don't fail. Right here in these facilities, they make a remarkable discovery. In the early hours of September 14, 2015, they record a message. Just a little chirp. But that chirp is epic, monumental. The signal traveled a billion light years to reach us. It started far, far away. And what it tells us is this. Somewhere in the cosmos, over a billion years ago, two massive black holes circle each other in a fatal encounter. Closer and closer they come, swirling faster and faster, until finally they slam together. Black holes create waves that spread outward, just like vibrations on a drum, or ringing in the fabric of space itself. The collision creates a massive blast, putting out 50 times as much power as the entire visible universe. It sends out a wave, not of heat or light or sound, but of gravity. This gravity wave is moving its way through the universe at the speed of light. The wave races by stars. On the young Earth, supercontinents are forming. Microscopic organisms have just appeared. The gravitational waves from the two massive black holes colliding continue to wash over one galaxy after another. Dinosaurs are roaming the Earth. The gravitational wave is still moving. And then it nears the Milky Way galaxy. The Ice Age is just beginning. The gravitational wave reaches nearby star systems. The wave approaches Alpha Centauri. At midnight on September 13, 2015, is as close as Saturn. Finally, over a billion years after the black holes collide, the gravitational wave reaches us. It strikes a pair of revolutionary detectors, the sites of the daring experiment. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. The experiment, 50 years in the making, has finally hit the jackpot and opened an entirely new way to view the universe. For hundreds of years, almost everything we've observed in space has come to us in some form of electromagnetic energy. This little chirp and the detectors are different. What hits the Earth in September 2015 is a gravitational wave that squeezes and stretches the very fabric of space. It produced no light. No telescope could ever see the collision. We needed an entirely new kind of observatory to detect it. That way is new and direct evidence of one of the strangest mysteries in our universe, black holes. Most of us have heard they're invisible, powerful. You're talking about things that are a billion times the mass of the sun. Bizarre, physical entities with infinite density. No beginning, no end. They pull things, including light. Approach one, and time itself begins to change. Gravity is so intense that a moving clock will tick slower. Time will become so slow for you that you will watch the entire future of the universe unfold before your very eyes. Fall in, and you'd be squeezed as thin as a noodle. Today, we know more about black holes than ever before. But the more we learn, the more mysterious they become. They're the most exotic objects in the universe, and we don't have the physics to describe them. You might think a black hole is like this, an object. But it's not. It's a hole in the fabric of space, a place where there is nothing, nothing except gravity, gravity at its most intense and overwhelming. So black holes are all about gravity, gravity at its most extreme. What exactly is gravity? We're all familiar with gravity. It rules our lives. But even so, for a very long time, how gravity actually works was one of the greatest mysteries. Over 300 years ago, Isaac Newton was fascinated with the behavior of moving objects. Eventually, he figured out his laws of motion. They work so well, we still use them today. But Newton's laws can only describe gravity's effects, not explain what it is. Here's where Albert Einstein comes in. Like Newton, he thinks about objects in motion, and he wonders what gravity actually is. Is it a force, or could it be something else? Here's what concerns Einstein. Take this apple. I can't move it without touching it. But if I drop the apple, it moves toward the earth. But what if I take my hand away, and the floor, and the basement, and the floor below that? Then what happens? The apple just keeps falling. Einstein realized that gravity had something to do with it. Do with falling. Now, if I throw the apple, it falls along a curved path. But imagine I can get the apple moving much faster. Eventually, if I get the apple moving really, really fast, say 17,000 miles an hour, its curved path touches the curve of the Earth. The apple is in orbit, falling freely, just like the International Space Station and the astronauts inside it. According to Einstein, the apple and the space station and the astronauts are all falling freely along a curved path in space. And what makes that path curved? The mass, the Earth. Einstein came up with a supremely simple concept, and that is that space and time is bent by the Earth and by the Sun, and by all the objects in the world. So according to Einstein, the mass of every object causes the space around it to curve. And that was Einstein's conception. There are no forces in it. There's just objects bending spacetime and other objects following the straightest line through it. All objects in motion follow the curves in space. So how does the Earth move the apple without touching it? The Earth curves space, and the apple falls freely along those curves. That, according to Einstein's general theory of relativity, is gravity, curved space. And that understanding of gravity, that an object causes the space around it to curve, leads directly to black holes. But it's not Albert Einstein who first makes the connection between gravity and black holes. It's another scientist. Karl Schwarzschild was a German astronomer, head of the Potsdam Observatory in Germany. Ever since he was a teenager, he'd been calculating complicated features of planetary orbits. As Einstein unveils his theory of gravity in 1915, Karl Schwarzschild is in the German army, calculating artillery trajectories in World War I, and just weeks after Einstein presented his papers, Schwarzschild, then on the Russian front, quickly got a copy and was mapping the gravitational field around a star. Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly. But Schwarzschild isn't done. In his solution to Einstein's equations, he discovers something Einstein himself had not anticipated. Schwarzschild said, "I can calculate this strange distance from a gravitating object that represents a kind of a boundary." Schwarzschild mathematically concentrates a mass, for example, a star, into a single point, and he calculates how that mass would bend space and curve rays of light passing nearby. As he through his mathematics aimed particles of light or matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped. Schwarzschild has discovered that a concentration of mass will warp space to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light. Once you go across that boundary, even if you can sail through, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time. What Karl Schwarzschild discovered is that any mass compressed into a small enough space creates what we today call a black hole. But Albert Einstein, whose own theory of gravity predicts such a thing, cannot believe it can happen in the real world. Einstein didn't think that nature could act like this. He didn't like this idea. Karl Schwarzschild becomes ill and dies before he has a chance to further investigate his own discovery. 2.5 years later, in November 1918, World War I ends. The strange theoretical sphere discovered by Karl Schwarzschild seems destined to be forgotten. Nothing but a curious historical footnote. But in the coming decades, physicists learn more about the atom and about how fusing atoms powers stars, a process called nuclear fusion. Some begin to wonder if something like a black hole could actually come from a star, but not just any star. It would have to be big. Stars are born in litters, and you get a distribution of sizes and masses. Thousands of little stars and a few big stars. Some are very big stars. Incredibly massive. Stars are in many ways living creatures. Like humans, they have life cycles. Investigating stars' life cycles in the 1930s, two visionaries, Subramanian Chandrasekhar and Robert Oppenheimer, discovered that the most massive stars end their lives very differently from smaller ones. The life cycle of a star really depends on its mass. The mass of a star determines what's going to happen after it finishes burning its hydrogen fuel. All stars start out burning hydrogen, the lightest atom, using hydrogen atoms into helium, working their way up to heavier elements. Gravity wants to crush the entire mass of the star, but the enormous energy released by fusion pushes outward the star from collapsing. Stars are stable because we have an outward moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity. Smaller stars can't fuse elements heavier than helium, but in the most massive stars, fusion crushes heavier and heavier atoms all the way up to iron. Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out. Iron is a dead end for stars. Fusing atoms larger than iron doesn't release enough energy to support the star. And without enough energy from fusion, keeping the star inflated, there's no energy left the crushing force of gravity to fight, and gravity wins. And so the entire star collapses. Very rapidly, collapses. Trillions of tons of material come crashing down, hit the dense core, and bounce back out, blowing off the outer layers of the star in a massive explosion called a supernova. The more mass, the more gravity. So if the remaining core is massive enough, gravity becomes unstoppable. There's no known force to prevent the collapse to an infinitesimally small stuff. Gravity crushes the stellar core down, smaller and smaller and smaller, until all its mass is compressed in an infinitely small point. A black hole. The theory makes sense, but most physicists at the time remained skeptical about black holes. Einstein and Eddington, all the preeminent astrophysicists in the 1930s or 1950s, did not believe that they were actually real. It remained a solution, but also a mathematical enigma for a very long time. So it took a long time for people to even start looking for these theoretical black holes. It's not until that the idea of a supernova creating a black hole is taken seriously. Princeton physicist John Muller, who had originally been a skeptic, begins to use a name from history for these invisible objects: black hole. Still, no one has ever detected any sign of a black hole. Then in 1967, graduate student Jocelyn Bell discovers a strange, extremely tiny dead star that gives off very little light: a neutron star. The cold remains of the stellar corpse, the neutron star, gives astronomers more confidence that black holes, much heavier dead stars, might also exist. A century after Carl Schwarzschild mathematically showed that black holes were theoretically possible, scientists have identified a natural process that might create them, and the death of light. So these giant supernova explosions of extremely massive stars could make black holes. Any star that is born with a mass that's about 10 times the mass of the Sun or higher will end in a black hole. So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone. So what are these invisible stellar corpses like? Imagine I'm exploring space with some advanced technology for interstellar travel, so that we can visit a black hole, maybe one in our own galactic neighborhood. This particular black hole isn't very big, only about 10 solar masses, meaning 10 times the mass of the Sun. And like all black holes, it has an event horizon, a distinct edge to the darkness. That's the boundary Carl Schwarzschild first discovered. Gravity is so strong that nothing can escape, not even light. And that's where we're going. As we get closer, some very strange things begin to happen. Look at the edge of the black hole. See how the image of distant stars is distorted and smeared into a circle. That's gravitational lensing. The black hole's extreme gravity bends the path of light passing by so that a single point of light, like a star, briefly appears as a ring around the event horizon. I'm now deep in the black, and we're going to start experiencing the effects. The extreme gravity actually slows down time relative to the Earth. From their point of view, I appear to be slower. But from my point of view, time on Earth is speeding up. Now let's say I want to get even closer by taking a spacewalk. The way the black hole slows down time is about to get even more pronounced. Track the changes I'm about to experience. From here, I can see the shadow of the event horizon approaching. But watching from the ship, the closer I move toward the black hole, the more slowly I appear to move. It looks as though I'm frozen in time. For me, everything is completely normal, even when I reach the event horizon. If you waited long enough, maybe millions or billions of years, the ship would finally see me disappear. And that's the last you'd see of me. What's inside a black hole? That's still a mystery. And even if I find out, I can never go back and tell you. But I can say this: black holes may be dark from the outside, but inside they can be bright. I can watch the light from a galaxy that's fallen in behind me, and that's the last I'll ever see. Unfortunately, the fun is about to end. Now that I've crossed the event horizon, I'm falling towards the center, where all of the mass of the black hole is concentrated. And I'm beginning to get stretched. As I fall in, the gravitational pull at my feet is stronger than at my head, and my body is starting to get pulled apart. I'll be stretched as long and thin as a noodle, spaghettified, and ultimately I'll end up completely disintegrating into my fundamental particles, which are then crushed to an infinitely small point. Singularity. Maybe the black hole, less than 40 miles across on the outside, is as big as a universe on the inside. And as I pass through, my particles will join the primordial soup of a new beginning. So that's what theory tells us we might experience if we could travel to a black hole. How can we know for sure? How do you investigate something you can't even see? There are ways to investigate if something is happening somewhere, even if I can't see that thing directly. Take Yankee Stadium. What's happening inside there? Is there a game going on? I can't see the field. I can't see any players or baseballs or bats. but I can definitely tell if there's activity around the park. It's pretty clear something is going on. It might seem obvious, but whatever it is, we can learn a lot just by observing the happenings around the stadium. These do look a lot like baseball bats. That's the way we investigate black holes, by observing the effect they have on their surroundings. How might a black hole reveal itself? Starting just before World War II, two monumental discoveries are about to radically change astronomy. In 1931, Bell Labs engineer Carl Yansky picks up mysterious radio waves emanating from deep space. Then the sky gets even stranger when scientists mount Geiger counters on captured German rockets and discover the cosmos is also full of X-rays. These discoveries give astronomers important new tools that will revolutionize the hunt for black holes and dramatically expand our vision. What our eyes can receive is a very narrow part of the electromagnetic spectrum. If the electromagnetic spectrum were laid out along the Brooklyn Bridge, the portion we can see with our eyes would be just a few feet wide. Electromagnetic radiation includes waves of many different frequencies: radio waves, microwaves, infrared and X-rays, and gamma rays. Radio and X-ray astronomy open up the sky, revealing dim or even invisible objects blasting out powerful energy no one knew was there. They began to realize that this very placid thing that we see out there, all this very quiet thing that looks like nothing is happening, and the only thing that's moving is the planets, found out that there was madness going on. There was chaos out there. X-rays come from the high-energy end of the spectrum. What is creating all this energy? This much is certain. Whatever the source, it is invisible to ordinary telescopes, and it is hot. X-rays come from things which are at temperatures of millions of degrees, in tens of millions. One of the first of these X-ray sources to catch the attention of astronomers is named Cygnus X1. Cygnus, it was in the constellation Cygnus. X, it was an X-ray source. One was the first one he found. In 1970, Paul Merton is a young English astronomer trying to secure his next job. Merton works in a 15th-century castle surrounded by telescopes, the Royal Observatory. Using the largest telescope in England, he begins searching the area of the constellation Cygnus, the Swan. He decides to hunt for pairs of stars are called binaries. They may sound exotic, but they're not at all uncommon. Many of the stars we see, perhaps half, are actually binaries, pairs of orbiting stars locked together by gravity. But Broden wonders, is it possible there are binaries where only one of the stars is visible? Merton thought that maybe there was a kind of a star system in which was a star, an ordinary star that made light, and then there was another star nearby that made X-rays. The telltale sign of the binary is that the stars are moving around each other. So Merton begins searching for a visible star that shows signs of motion. Sometimes it's coming towards you. Sometimes it's coming away. Sometimes it's coming towards you. Sometimes it's coming away. When the star is moving towards us, it appears more blue, as the wavelength of its light gets shorter. Moving away, it appears more red as the wavelength of its light gets longer. This is known as Doppler shift. After looking for color changes in hundreds of stars in the area of Cygnus, Merton spots a possible suspects, a visible star whose light is shifting, as though moving around. It very clearly was a binary star, a double star. The star was moving around and around with a period going around once every 5.6 days. But whatever it's going around can't be seen. There was no trace in the spectrum of the second star. There was one star there, but there wasn't a second star there. Merton has a binary pair in which only one star is visible. The second object in its X-rays has enough mass and gravity to dramatically move a star, but gives off no light. Could it be the corpse of a star massive enough to become a black hole? A crucial issue in deciding whether Cygnus X1 was a black hole was to measure the mass of the X-ray emitting objects. It would have to be very massive, at least 3 times the mass of our Sun. If not, it's probably just a neutron star, a collapsed star that's dense but not heavy enough to be a black hole. So the observers needed to come up with a conclusion that the dark object, the X-ray emitting objective of Cygnus X1, was heavier, hopefully substantially heavier than 3 solar masses. From his observations, Merton is able to make an estimate of the mass of the invisible partner, and the answer came out to be 6 times the mass of the Sun. So there was a story then that Cygnus X1 was a black hawk, and the key to the argument was that the mass of the star you couldn't see was more than 3 solar masses. When I'd finished writing it all up, I sat back and thought, it's a black hole. This would be the first actual detection of a black hole. It's a huge claim, and Merton will have to convince skeptics, starting with his boss. The Astronomer Royal, Sir Richard Woolley, didn't really believe in black holes. Sir Richard Woolley was nervous about the scale of the discovery. Sir Richard Woolley was working with a fellow scientist, Louise Webster, and were modest about the claim that they were making because they suspected what people would think it to be unbelievable. If you look at the paper that they published, it mentions the word black hole only once, right at the end. We think this might be a black hole. The Paul Merton and Louise Webster paper appears in September 1971. Other astronomers agree it could be a black hole, but no one knows for sure. 3 years later, Kip Thorne and the noted British physicist Stephen Hawking make a now famous wager about Cygnus X1. They made a bet as to whether Cygnus X1 really was a black hole or not. The bet is partly in jest. Both men hope it is a black hole, but Hawking, not wanting to jinx it, bets against his own wishes. Stephen claims that 6-1 is not a black hole, and I claim it is a black hole. So they agreed to that bet in December 1974, and gradually the case that it really was a black hole became stronger and stronger and stronger. Stephen Hawking conceded the bet. Thorne came back from Russia and discovered that he had won the bet when he heard that Hawking had conceded that Cygnus X1 was, by all evidence, a black hole. Now by 1990, the evidence of Cygnus X1's mass may be strong enough to settle a bet between two friends. But the original estimate wasn't precise enough to be definitive. In order to calculate mass, Hall-Merton had to rely on rough estimates of the distance to Cygnus X1, which varied by a factor of 10. And the question wouldn't be answered for another years, until astronomer Mark Reed became intrigued by the puzzle. Reed is an astronomer at the Harvard-Smithsonian Center for Astrophysics when he sets out to conclusively that Cygnus X1 is a black hole by measuring its precise mass. But how can you measure the mass of an invisible object? Using laws developed by German astronomer Johannes Kepler in the 1600s, it's possible to calculate the mass of a celestial object, but only if you know its distance. Distance in astronomy is absolutely fundamental. If you don't know distance, you don't know what the object is. It could be a very nearby firefly-like thing. It could be a very distant, huge star, much, much bigger than the Sun. So to get the true, precise mass of Cygnus X1 and confirm that it is a black hole, Ray needs to know how far away it is, but how can he measure the distance to a star? The secret lies in a familiar phenomenon, parallax. It's what our eyes and brains use to see in 3 dimensions. You can put your finger up at arm's length, look at it, and close one eye, closing my left eye. And I'm looking at my finger relative to the wall in the back. There. Now if I open my eye, close my right eye, I see my finger has appeared to move with respect to the original position. That's because our eyes are separated. We view from different vantage points. To use parallax to measure distance to an object in the sky, astronomers let the motion of the Earth provide the 2 different vantage points. Imagine Cygnus X1 is right here, and the Earth and the Sun are over there. And the Earth goes around the Sun once a year. And in the springtime, the Earth ends up on one side of the Sun. And we observe Cygnus X1 along the ray path like this. And 6 months later, the Earth goes around the Sun. The other side, we get a different vantage point from Cygnus X1. Now he has a triangle that goes between the Earth at its two positions and Cygnus X1. We know the base of the triangle, the diameter of Earth's orbit, and the principles of geometry tell us that all we need to calculate the distance is the size of the angle at the top. And we measure this very small angle here at the point at Cygnus X1. And then from direct geometry, we can calculate the distance to Cygnus X1, and from that infer a very accurate mass. The concept is simple, but Cygnus X1 is so far away that the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle spanned by Abraham Lincoln's nose on a penny in San Francisco viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution. We take 10 radio telescopes that are spread across the continent in the US and to Hawaii and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we simply size in a computer. Telescope has a diameter of the size of the Earth. That gives you incredible angular resolution. Using this technique, Reed team determines that Cygnus X1 is 6,000 light-years away. They were able to determine that the mass is about 15 solar masses. Easily a black hole. 40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole. So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit with my imaginary spaceship, what would we see? Distance to Cygnus X1 has been established at 6,000 light-years from Earth, and its mass is 15 solar masses, or 15 times the mass of the Sun. And Cygnus X1 is surrounded by an accretion disk, a disk-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, the particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays, and it's those X-rays that first led astronomer Paul Merton to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up, but not all of it. Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating half the pasta ends up on the floor, half of it may be on the ceiling, and some of it in the mouth. One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams of particles and radiation stream outward from Cygnus's north and south poles perpendicular to the accretion disks. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus. When gas gets to these high temperatures and produces the light, there's also a little bit of a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help these massive outflows from black holes form in columns. Powerful hoses, if you will, that just spill matter out. So that's Cygnus XY. If we could see it up close, a growing, feeding black hole with huge jets, blasting particles way out into the universe. What was once a bizarre mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned-out corpses of large stars can travel inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds. Black holes seem like such a radical idea that we shouldn't accept it. But bit by bit, The evidence for black holes has gotten stronger and stronger, and we've seen these amazing things. At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. There are probably millions more of these massive stellar corpses in our galaxy alone. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking new discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hotspots emitting radio signals. The radio signals were coming from what looked like stars. Because these objects resemble stars, but were discovered through radio signals, astronomers named them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star, but the spectrum of a quasar turns out to be incomplete. They looked at it, and it was gibberish. It didn't look like there were any emissions from elements that they knew. What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar's spectrum is the fingerprint of hydrogen. He noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the red. It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum. And that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have almost never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand, the light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speeds. The reason? It's the legacy of an event that occurred almost 14 billion years ago, the Big Bang. And ever since, the universe has been expanding, carrying with it all the objects it contains, including quasars. Almost no one had ever seen anything moving away at that high speed. This made this object almost the furthest away thing that had ever been seen, which meant the thing itself had to be so incredibly luminous, and you had to account for that. 2 billion light-years away, putting out the energy of 1 trillion suns each second. What could possibly create that? No one had any idea what could be powering these things. Where could all of this energy come from? If you work out through calculations, it can't be chemical energy. They knew it couldn't be nuclear energy. There's no way a quasar could be a star. No amount of nuclear fusion can possibly create that much star power. The only engine that could possibly put out that much energy is gravity. Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering, could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes? To produce that kind of energy, that kind of brightness, it has to involve a black hole. But not just any black hole. Whatever was the source. If the emission from a quasar had to be massive. How massive? Well, millions or billions of times heavier than the Sun. Millions or billions of times heavier than the Sun. Cygnus X1 is only 15 times the mass of the Sun. The black holes powering quasars are an entirely different category of black hole. Supermassive black holes. And supermassive black holes seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to home? The center of our galaxy, where any supermassive black hole would be found, lies in the direction of the constellation Sagittarius, the Archer. Now, Sagittarius, just any constellation. It's in the direction of the center of our own Milky Way galaxy. Since we live inside the Milky Way, We can't see the galaxy the way a space traveler would. The Milky Way is a spiral galaxy. Hundreds of billions of stars are drawn together into a gigantic disk. Our Milky Way galaxy is about 100,000 light-years across, but it's relatively thin, only about 1,000 light-years thick, and the whole spiral slowly rotates. Our solar system is near the outer arms. And here, 26,000 years from the Earth, is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars and lots of dust and gas. So that's the view of our galaxy from the outside. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky. Deep inside this band of stars and dust, could there be a supermassive black hole? In the 1990s, astronomers were determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez. Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy. The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the stars that are as close to the center of the galaxy as possible, which means using access to the largest telescope. The summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and low humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion. Think about looking at a pebble at the bottom of a river. The river is moving very, very quickly, and your view of that pebble is distorted. Like a river, the Earth's atmosphere is constantly changing, bending light like a funhouse mirror. To compensate for this, Keck pioneers the scientific use of a declassified military technology called adaptive optics. First, they shine a laser into the sky, creating an artificial guide star. The turbulent atmosphere distorts the guide star, but the computer knows what it should look like and adjusts the telescope mirror accordingly. So if you look at yourself in the circus funhouse mirror, you look completely distorted. And the goal of the adaptive optics system is to introduce a second mirror that's the exact opposite shape and make the reflection in the mirror flat again. Very deep inside the Keck telescope, the deformable mirror changes shape up to 2,000 times a second to reverse the atmosphere's distortion. And it has allowed us to take the sharpest images ever obtained of the center of the galaxy. The sharpness of those images allows Ghez to make out individual stars near the center, a huge advance in astronomy. She begins recording them in 1995. And every year since then we've taken an image. Just take a picture. Putting those annual snapshots together creates a time-lapse movie of stellar orbits. And what those movies reveal is astounding. The stars are whipping around the center of the Milky Way at phenomenal speeds. These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. To go that fast, the stars must be orbiting something extremely massive. The mass that we infer is 4 million times the mass of the Sun. What could be 4 million times the mass of the Sun, yet be completely invisible? Only a black hole. So this is the proof of a black hole. And not just any black hole, a supermassive black hole, silent and churning right in the center of our own galaxy. This is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe. A supermassive black hole 4 million times the mass of the Sun, and the very center of our own Milky Way galaxy? From a cosmic perspective, it's right next door. And it raises a profound question. There are billions of galaxies out there. If ours has a supermassive black hole at its center, and if quasars are found at the centers of their galaxies, what about the other galaxies? Are there black holes at the centers of other galaxies? If there are, how common are they? We simply didn't know. Could astronomers ever hope to find what lurks at the centers of other galaxies, millions of light years away, as GES did in our Milky Way? It would take another innovation in astronomy to make that possible. When the Hubble Space Telescope starts delivering clear images of distant galaxies, a team of astronomers gets to work. They become known as the nukers because their focus is galactic nuclei, the centers of galaxies. One of them is Todd Lauer. Step 1. We take a picture of a scene with the Hubble Space Telescope. It shows us where the stars in the galaxy are. It tells us its structure and exquisite resolution. The key to finding supermassive black holes is to learn how fast the stars in the galaxy are moving. Galaxies outside our own are much too far away to measure the speed of individual stars. But by analyzing the way light is shifted from blue to red at different points in the galaxy, astronomers can put together an average speed of stars orbiting the center. It's accurate enough to create a computer model. Second step is to try to model the observations. And we actually do that by building models of galaxies with what is known as Schwarzschild's method, developed by Princeton astronomer Martin Schwarzschild, son of Carl Schwarzschild. His mathematics first described the possibility of black holes. Martin Schwarzschild built a model of the galaxy that not only shows where the mass is, but also had how the stars are moving. For each galaxy they investigate, the nukers painstakingly build a computer model, and then using trial and error, adjust the parameters of mass and velocity, trying to make the model match the original observations they got from the Hubble. And we say, let's try a star here. Let's try one over here. Let's have it go around this way. Let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars orbit in this galaxy. Success is when observations of the model match the observations taken with the Hubble Space Telescope. But that doesn't happen. The models are missing something. We try it again and again and again, all with no black hole yet. Only when they add an enormous invisible mass at the galaxy's center does the model match the Hubble observations. Almost always, we have to put in a black hole at the center. We can't match the observations without a black hole in the model. Of roughly 36 galaxies modeled, all of them require a supermassive black hole. And since then, other observations have made us even more certain that supermassive black holes and galaxies go together. Every galaxy we've looked for one, we have found a supermassive black hole in its center. It's a stunning revelation. Supermassive black holes, once an entirely unexpected category of black holes, may be common. Not only the center of our galaxy, but of all galaxies. Take galaxy M31, also known as the Great Andromeda Galaxy. It's 2.5 million light-years away. On a clear night, you can see it from Earth. But even with the Hubble Space Telescope, we can't make out precise details of its center. So we're pretty sure there's something extremely massive hiding there. What if we could take a closer look? What if we can visit a galaxy far, far away, enter the outer part of Andromeda? We're still too far away to see what's lurking at the center. But we can make out a dense cluster of stars in the core. And that could be a sign that there's a giant black hole nearby. Billions of years ago, it would have been surrounded by gas and stars and other small black holes. The black hole may have powered a quasar feeding and blasting out blinding radiation. Over hundreds of millions of years, it would have consumed all the available gas and the closest stars. The black hole at the center of the Andromeda Galaxy is colossal. If it were dropped in our solar system, Mercury, Venus, Earth, and Mars would all be trapped inside the event horizon. That's big, but it's nothing compared to the sheer mass, 100 million times the mass of the Sun. And the destruction won't end there. Jupiter won't last long. The gravitational field of the black hole will grab hold and swallow it whole. Eventually, Saturn will suffer the same fate. The outer planets might survive, but in cold and dark orbits. This black hole rotates rapidly, distorting and dragging the fabric of spacetime. Like all black holes, the event horizon is completely featureless. Remember, there's nothing there. It's just a boundary that conceals the interior. But the accretion disk can tell us a lot about what's going on. That's the fiery ring of gas and dust around the black hole. Imagine if we could release a swarm of autonomous robots to explore the accretion disk. The disk is spinning at an incredible speed, as much as half the speed of light. If Jupiter moved that fast, it would complete its entire orbit in a few hours. The region around the black hole is a cosmic tornado. Now our swarm is caught in a whirlwind too. They're like tracers, going into the storm to map movement. The middle robot can send us images. It's following the leader like a race car speeding around the track. From here, the extreme warping of space-time around the black hole plays crazy tricks on our eyes. It looks like there's one accretion disk whipping around the equator and another arcing in under the poles. But that's an illusion. The black hole's extreme gravity bends the path of light emitted behind the black hole and makes it look like the accretion disk is both above and below. There's actually nothing around the poles. It's just the passing light rays. That's gravitational lensing again. Going much closer that horizon, the gravitational lensing would become so extreme that one of our robots could look straight ahead and eventually see its own back, the light forever trapped in an eternal circle. So that's our tour of the supermassive black hole at the center of the Andromeda Galaxy. Pretty amazing. Also amazing, nothing in the mathematics led scientists to imagine that black holes can get that big. As strange as they are, ordinary stellar mass black holes were at least predicted by theory. Supermassive black holes are a complete surprise. With stellar mass black holes, people thought about them from a theoretical perspective, and then we found them observationally. The supermassive black holes, this story has been inverted. We actually found evidence of them observationally first, and now we're working on the theory of how do these things come into being. We already know that stars can collapse to create ordinary black holes, but supermassives are bigger by many orders magnitude. Cygnus X1 is 15 times as big as our Sun. The supermassive at the center of our Milky Way is 4 million times as big as our Sun. The one in the Andromeda Galaxy is 100 million times as big as our Sun, and it's not the biggest, not even close. There are supermassives 10, even 20 billion times the mass of our Sun. How is it possible to make such gigantic black holes? Could supermassives have come from collapsed stars? That seems very unlikely. We don't know of any stars billions of times bigger than the Sun. We know about black holes you might get from a dying star. They have several times the mass of the Sun contained within, but millions of times the mass of the Sun. If that's the case, a dying star cannot have possibly made it. So do these supermassives, millions or even billions of times heavier than the Sun, somehow just grow, packing it on like voracious giants? The wild thing about black holes, they're constantly devouring anything that comes within their sphere of influence. So they grow. We believe that black holes grow by accretion of gas. And the way this works is that you have a lot of gas around in the center of a galaxy. And this gas would then assemble and form an accretion disk. The accretion disk is made up of hydrogen, helium, and other elements in a gaseous form. The immense gravity of the black hole pulls the gas in toward it. As it swirls around, it orbits closer and closer to the black hole, and the feeding begins. Stuff in the inner regions would get slowly pulled in, sped up, will reach the event horizon, and then that's it. Whatever gas crosses the event horizon disappears forever. The black hole has absorbed that material. It actually adds to the mass of the black hole. This is one way a black hole can grow, gradually nibbling gas and dust. But it's not the only way. Cygnus X1 has been slowly stripping material off a nearby star, a process that will likely go on for thousands or millions of years. But what if a black hole could rip an entire star apart in just a matter of years or even weeks? That would be and a team of space explorers is on the lookout. Orbiting up to 86,000 above the Earth, Chandra takes high-resolution images of objects that emit X-rays. A short-lived, extremely violent event called a transient, which fascinates James Galoshan. James is investigating a mystery discovered colleague Dasheng Lin. This blur on James's screen is actually a massive sudden burst of X-ray energy caught by accident. This little smudge popped up in the background of a Chandra image. And given its great distance, it's actually tremendously bright. Could it be a black hole caught in the act of being born and the violent collapse, a huge star, a supernova? Perhaps, but the intense radiation released by supernova would only linger for a few months. So how long has this mystery object been blasting out X-rays? To find out, they look at images of that same part of the sky taken an earlier date. No X-rays detected. But the X-rays are there just 3 months later in July. And the powerful bright signal has continued for more than 10 years. From July 2005 to the present, far too long to be a supernova. So what could it be? A black hole that's not feeding, is quiet and completely dark. It won't show up on any telescope. But a black hole that is feeding is different. When it feeds, it blasts out X-rays. So could this be a black ball that's suddenly begun devouring something big? What effect will this have on anything that comes near? What would it do to a star that wanders too close? Well, it will consume the star layer by layer, ultimately devouring the entire star. Unlike Cygnus X1, this is no mere nibbling. This is a 10-year feeding frenzy, a massive black hole devouring an entire star in a cosmic blink of an eye. It's the result of a chance collision. When an unlucky star wanders too close, the black hole's extreme gravity actually rips it apart. Gravity from the black hole will progressively and stronger as the star gets nearer. And at that point, the star will begin to deform. It's called tidal disruption. It's similar to the way our moon's gravity easily moves all the world's oceans. The tides caused by a black hole would be billions of times stronger and much more violent. You have these events where a star could be ripped apart by a black hole. So you would see sort of a plume of light from the last gasp of the material in the star. But there is a chance for some part of the star to escape, as James illustrates. As the star is elongated by the black hole's tidal forces, it will essentially be feeding the black hole at the same time as half of it is trying to escape. So everything above this point approximately will have the chance of leaving the galaxy. It's moving that rapid, and everything below this point will fall back onto the black hole and eventually be consumed by it. So this is another way for a black hole to gain weight. Unlike the slow, steady nibbling of Cygnus X1, this black hole is devouring most of an entire star in one gulp. But whether a black hole feeds suddenly by swallowing half a star or steadily through accretion, astronomers still face a problem when they try to understand how supermassives got so big, the timing problem. The trouble begins with the very oldest supermassive, quasars, those very bright, very distant, and ancient objects first discovered in the early 1960s. The conundrum was when we started finding these quasars, very bright quasars, very early on in the universe. They're giving off so much energy that they have to have very massive, supermassive light levels at their center. But quasars are extremely far away, which means they're part of the very early universe, which began nearly 14 billion years ago. Bright quasars, 600 million years after the Big Bang, a fraction of today's age. And they're enormous. So billion solar mass black holes, these behemoths, had to be in place when the universe was about a million years old. Now you have a problem because you have to grow something really big, really fast, and you are bumping up against all sorts of physical limits. Whether a black hole is nibbling or gulping down its neighborhood, it turns out that accretion, how black holes feed, has a speed limit. Named after English astronomer Arthur Eddington, The Eddington limit will not allow a black hole to feed too fast because of the light blasting out from its own accretion density. Light has a pressure, so photons can impart a force on something. We see this in winds from stars. Light is pushing out gas, so there's a limit to how fast you can feed a black hole. So given the speed limit, how did early supermassives, quasars, get so big so fast? Could there be a way to bypass the speed limit entirely? The problem is still time itself. How do you grow them to 1 billion solar masses so quickly? What are the conditions that you need for that kind of growth? Some scientists are now asking, what if there's a way to create a black hole that's already much more massive from birth, giving it a head start? If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growth is not as acute. The answer, some believe, is to create a black hole directly from a cloud of gas, a scenario called direct collapse. It starts with gas clouds made of hydrogen, helium, and other elements, the same raw materials from which stars are born. The denser clouds will start to collapse under their own gravity. As they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments. Those fragments continue collapsing until the hydrogen atoms within them begin to merge. Nuclear fusion begins and stars are created. But what if a giant gas cloud collapsed without making stars? Realize that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole. It's something we've all seen in nature, from tornadoes to bathtubs, a vortex, but on a supermassive scale. If you're in a bathtub and you pull the plug out and you see the water flowing in a vortex very fast down to the center, that's exactly what happens. Direct collapse might be a way to create very large black holes, earthy in the universe, or enormous gas clouds, completely skipping the star stage, because they would be so large already at birth. These direct collapse black holes would have a head start, helping them to quickly grow into the enormous young supermassives we see in the distant universe. You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the Sun, and that they form from the get-go with that mass. Direct collapse may explain how enormous early supermassives got their start. But there's another fundamental question about supermassives. What is their role in the universe? Is their existence just a matter of chance, or are they connected some larger way to the very structure of the cosmos? Supermassive black holes don't exist in isolation. They seem to live in partnership with galaxies, collections of millions, billions, or even trillions of stars bound together by gravity. Galaxies are the fundamental building blocks of our universe. So are the supermassive black holes at their centers, somehow fundamental to their very existence. We now just assume every galaxy, even ones we have yet to confirm, will have a supermassive black hole in their center. It could be that instead of simply being oddities, that they are a key component to galaxies and key components to the universe. We've come to realize that they likely inhabit the centers of all the galaxies. That can really only happen if there's some symbiotic relationship between the evolution of the galaxy and the supermassive black hole in its core. What could that relationship be? One intriguing clue relates to size. The bigger the galaxy is, the more massive the black hole appears to be. So these black holes at the center seem to know about their larger scale environment. So which comes first? First, the galaxy or the supermassive black hole? It's not that simple. It appears they somehow grow in tandem. It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process, and that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock. The way galaxies grow is by forming new stars from clouds of hydrogen gas. Gas is essentially the fuel for star formation, just like gas is the fuel for our cars. And so, if you run out of gas, you run out of new stars. So are supermassive black holes somehow interfering with star formation? When a black hole is growing, tremendous amounts of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas, and gas that's too warm will not form stars anymore. The heat produced by a growing black hole makes it impossible for stars to form nearby. And so one way that growing black holes influences the host galaxy is by quenching star formation at the center. In effect, the growth of the supermassive black hole determines whether or not its host galaxy grows or stagnates. They have a kind of eating phase and then a napping phase. So they seem to be involved with the formation of the galaxy in that way, and thus stabilizing of the galaxy at the same time. So these mysterious supermassives may actually control the building of the universe, not so much by their size, but by the way the energy they generate shapes galaxies. By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically how much power the galaxy gets, and at what time, as it assembles, seems to be dictated by the central black hole. So they might well be the key players in the universe. Humanity's most powerful telescope ever, the James Webb, is designed to look in the infrared, allowing it to see farther back in time than Hubble, getting a look at the first stars and galaxies that formed after the Big Bang. Hopes are high that the James Webb Space Telescope will help solve many of the remaining mysteries about the earliest supermassive black holes. The James Webb Space Telescope is tuned to observe the early universe when galaxies were being born. It could give us deeper understanding of how you end up with a supermassive black hole in your galaxy to begin with. And the James Webb Space Telescope isn't the only new development that promises to solve some of the mysteries around black holes. A group of scientists, led by Shep Dollman, is now attempting the impossible, to take a picture of a black hole. The project is called the Event Horizon Telescope. The basic goal of the Event Horizon Telescope is really to see the unseeable, is to bring into focus something that science has told us for many, many years is precisely something we can't observe, being a black hole. Their primary target is Sagittarius A star, the supermassive in the center of our Milky Way galaxy. They're using a global network of radio telescopes. But if black holes are invisible, what exactly do they hope to photograph? What we're trying to photograph really is the shadow. So as this gas around the black hole swirls inwards and actually hits the event horizon, it leaves a silhouette, a very well-defined shadow on the surrounding light. So really, it should look like a donut with its very well-defined hole. And that's the picture that we are after. The team has conducted their first observing run and is processing the data now. It's hoped that these new technologies will give us an unprecedented view of black holes in our universe. But there is one new technology that is already delivering results. And that brings us to LIGO, flare, and the black hole drama to an idea that took root way ahead of its time, gravitational waves. With general relativity, his theory of gravity, Einstein predicts that when an object moves, it can create ripples in space and time, an actual squeezing and stretching of space and itself. One of the holy grails of 20th century physics was to detect these gravitational waves. That was not easy to do with general relativity because all the effects that you could think of were infinitesimally small, very, very difficult to measure. The thinking was if gravitational waves could be measured, it would confirm Einstein's prediction, and there could be an added benefit. It might also prove the existence of black holes by detecting gravitational waves, and help solve the mystery of how supermasses grow, but how to detect gravitational waves. In 1970, the problem caught the attention of a young experimental physicist, Ray Weiss. So how to measure the extremely tiny expansion and contraction of space? Ray's idea was to use light. Send a beam of light from one place to another and measure the time it takes to get there. That's how the exact distance to the moon was calculated. Bouncing a laser beam from the Earth off a mirror left behind by Apollo 11 astronauts. From the duration of the round trip, scientists could determine the distance. Ray came up with an ingenious design for it that uses lasers and mirrors to detect the faint expansions and contractions of space that would be caused by a gravitational wave. It's called a laser interferometer. It works by firing a laser into a splitter. Half the light continues straight ahead towards one mirror, while the other half is sent towards another mirror. The distant mirrors bounce the light beams back, where they rejoin at a detector. If the distances two beams travel are exactly the same, the system is designed so the two beams cancel each other out. The detector sees nothing. You set the track to measure the gravitational wave. Now comes the gravitational wave that's coming, let's say, at the structure. If a gravitational wave passes through, it briefly changes the length of the arms. The light beams no longer arrive back at the same time to cancel each other out. A gravitational wave hits. Light appears at the detector. The trap has sprung. That's the basic idea. It's a very straightforward measure. A clever idea, and simple in principle. But the difference in length between the two arms would be tiny beyond imagining. How tiny? Well, take the size of an atom. It's less than that. Go down by a factor of 100,000. That's the nucleus of an atom. It's less than that. It was 100 times below that. Everybody's initial reaction to the idea was, this is going to be impossible. In 1973, Kip Thorne puts his skepticism on the record in a classic textbook, doubting it will ever work. But Kip has never heard Ray Weiss explain his plan in detail. But it will take 40 years, enormous sums of money to bring Ray and Kip's vision to reality. Getting LIGO funded was extremely controversial. Hundreds of millions of dollars to detect a signal that had never been seen before. Many people feared that LIGO would suck the money out of the room. So there was a lot of controversy, which everybody could agree on. This was extremely difficult. With such a sensitive instrument, one of the biggest challenges is noise. Ground motion, seismic motion, acoustics, noise, sound, everything would tend to move that mirror. Turns out, even the emptiness of a total vacuum creates a potentially crippling problem. At subatomic distances, the weird randomness of the quantum world causes a ruckus in the mirrors. Quantum noise is due to quantum fluctuations. These mirrors are doing what an electron does inside an atom. And they're jiggling around. Exquisite sensitivity, extreme vacuum, hundreds of thousands of electronic circuits. LIGO is one of the most complex instruments in the history of science. And as a final means of eliminating false signals, they build not one, but two. Complete one in Washington State and another in Louisiana. And so the LIGO designers did it right. They designed more than one detector, separated from one another by great distances, so that if you detect something in one and not in the other, then go back and check your electronics. Early fall 2015. Both locations are operating, but the first official science run has not yet begun. They're still testing. In the early hours of Sunday, September 14, 2015, a scientist in Louisiana, Robert Schofield, has been working all weekend doing final calibrations. He has one last test, but it's late and the equipment is not cooperating. It was about 4 or so in the morning, and we still had about another hour of work to do. Yeah, things aren't working so well, and I'm really tired. Let's not do this last hour. So we call it a night, and 40 minutes later, in the silence, they open the door to history. Powerful gravitational wave rumbles through both detectors, Louisiana and Washington. If Robert Schofield had not decided to work 40 more minutes that night with the instruments in test mode, A signal that had been on its way for 1.3 billion years would never have been recorded. A signal so strong that you can see it by eye in the data. It was too good to be true. But it was true. In fact, it was loud and surprisingly clear. The signal lasted less than a second, but in that briefest of moments, it delivered a positively profound message more than 1 billion years in the making, proving the existence of black holes. So what we saw in the signal involved oscillations of the mirrors that were slow at first, became faster and faster and faster. And this was precisely the kind of behavior that you would expect from gravitational waves caused by two black holes going around each other, spiraling together. Two massive black holes, one 29 times the mass of the Sun, the other 36 times the mass of the Sun, whipping around each other hundreds of times a second, finally completing their act of mutual destruction by merging, creating a single larger black hole of 62 solar masses. The violent merger converts some of the mass into an apocalyptic and elusive energy beyond anything ever before witnessed. The collision, in effect, creates a very unbearable storm for the shape of space and time. So you had taken three suns, you had annihilated it completely, converted it into gravitational waves and power. That's 15 times higher than the output power of all the stars in the universe put together in a fraction of a second. But the most powerful explosion that humans have ever had any evidence for, with the exception of the Big Bang. Since that very first signal in September 2015, LIGO has detected several more collisions of black holes. In October 2017, Weiss, Kip Thorne, and LIGO's former director, Barry Barish, received the Nobel Prize. The LIGO discoveries proved that black holes can merge. One way they can grow bigger quickly. More and more evidence of these merging black holes tells us there are a lot of these stellar black holes around that they can find each other and merge. And the discovery opened an entirely new way of serving universe. I've always thought of astronomy as an observational field where we are looking at radiation. We are seeing things. But this is not radiation. This is something much more fundamental. These are sort of fundamental tremors in space-time itself. We can now hear the universe. For the first time, astronomers have simultaneously seen and heard a cosmic event. In August 2017, LIGO detected gravitational waves from a collision of two neutron stars. Black holes are empty space, but neutron stars are dense stars that can crash together and light up the skies. And telescopes and satellites around the globe pointed in the direction of the sound. The world saw fireworks and an explosion, collision, and afterglow. Possibly, the collision resulted in the creation of a new black hole. As we observe the formation of a black hole, there is much we will never know. Because so much about black holes is irretrievably out of our reach. We can never know where they came from, or what's their history, but we can imagine their future. The number of black holes in the universe is increasing, and they're getting bigger. Stars collapse, black holes feed and emerge, new ones form. Could it be that one day, everything will end up inside them, and they will be the universe? Untold trillions upon trillions of years after this happens, and the last bits of matter cross their event horizons, black holes themselves may radiate away and vanish forever. In this reality, their mysteries are many, and we're just starting to unlock the secrets of these strange, powerful places. But one thing is certain, black holes will continue to intrigue us, tantalize us, and challenge both our science and our imaginations.